welcome back to the final talk of today's afternoon. We have Christian and Beneš talking about random walk losing rotational symmetry.
All right, thanks. Thank you very much to the organizers for inviting me. I'm very happy to be here. I think this has been an amazing conference so far, very well organized and great talks. I'm also very happy that the conference is not taking place around Greg's birthday because my wife will be in her 9th month of pregnancy at that point. And so choosing between coming to the conference and not being away from New York would have been maybe more difficult. So, I was a student of Greg Lauder's. I guess Brent was very happy to be the first of his students to give a talk here. So for symmetry, I'm happy to be the last. So I started working with Greg just before the SLE explosion, and so more or less the first thing he made me do was read his green book, which so the green book is the one on intersections of random walks. A book I really enjoyed a lot, even though I think I almost didn't understand anything at the time. Maybe I understand a bit more now, but okay, it's really a wonderful book, I think. And so I wanted to talk about random walk today, actually simple random walk. And Greg mentioned a meta theorem for linear algebra earlier. I don't know if there is one for a simple random walk as well, that everything that can be proven has been proven. I hope not. Okay, so I hope not. If yes, then likely there will be a nightmare scenario where after 5 minutes somebody gets up and says, okay, all of this is known. Okay, so maybe wait until the end of the talk if you realize this. Okay, so let me just it'll be a very elementary talk, well, somewhat computational, but I try to make it as little computational as possible. So let me just start maybe with the motivation. So Brownian motion is very nice. We can compute lots of things for it thanks to the transition density. And so there's one of these probabilities which is, I guess, a moderate or large deviation is probably in the Brownian case, which looks particularly nice. And that's the two-dimensional probability of being outside of a disk. Okay, and at some point I needed the same thing for random walk, and there are lots of bounds, but no exact probabilities. And morally, the corresponding probability for random walk should be the same, but is it really? So that's what. Well, that we'll know at the end of the talk. But to answer this question, we need the local central limit theorem, which basically does the same thing as, how does this work? As this for random walk, a probability for every time and every point. Okay, so well, what should it be? Well, we have a tendency to think of Brownian motion and random walk as being the same thing. So we should be able to use the Brownian density to answer this question. And so random walk at time n in d dimensions looks like Brownian motion at time n over d. And the reason for this division by d is basically that Brownian motion can cut corners. And you can basically just see this out of the central limit theorem, the d-dimensional central limit theorem. So, so these probabilities should be more or less the same. And then there's also the issue of parity with simple random walk. So we have to multiply by 2 to account for the fact that there's no chance at time n that we're hitting points of parity that's not the same as n. Okay, so then this is what we should get. And if we sum this, okay, so if we do this not too carefully, we can get log asymptotics of this form. Okay, so the central limit theorem says that this basically works for x bounded by some constant times root n. It doesn't say much about what happens outside of that range. So it turns out it's true for a larger range of values of x, but not arbitrarily large. Okay, so Greg's books are color-coded, so. So in intersections of random walks, so here's the main result for simple random walk in ZD, and it basically says exactly what the heuristic argument suggests. With two error terms, one which is a bit better if we just look at time, the other one is a bit better if we also look at space. But these results, of course, as soon as x is of greater order of magnitude than root n, the main term decays exponentially and the error terms aren't useful anymore. Okay, so there's another result in the same book which actually goes a bit further, and it says that if you take x of order n to the pretty much up to 2/3, the same approximation holds, and it's an asymptotic result. Okay, so then there's an improvement on this in the Gray book, which basically extends this to the disk of radius n to the 3/4. Okay, and this is in one dimension, but okay, it turns out the same will be true in higher dimensions as well.
I'll just make one comment right
Yep,
now,
sure.
just for people to confirm. These are not my original theory.
Right, yeah.
Yeah, okay.
Okay, so all right, so let me just say a few words about this. So I mean, lots of people have worked, and I'll say a word about that on local central limit theorems. Let me just say a few words about rate functions. So basically, rate functions are functions which basically describe the behavior of this right here. And so they're functions which tell us what the log asymptotic behavior of the random walk is. Okay. And then there's a theorem by Kramer which tells us that basically for nice random walks we can always find such a rate function which describes exactly the behavior of this probability for essentially any x. And there's a nice computational formula. Well, it's nice in the sense that sometimes one can compute it explicitly, though it can be a little bit difficult to work with. Okay. For a simple random walk, it's very nice. Okay. All right, and so then there are many books, actually. The one by Borovkov and Borovkov is maybe something like 800 pages long, and it does a bit more than that, but it basically gives local central limit theorems for any setting you might dream of. So strong moment conditions, very weak moment conditions. Okay. But often these results are given in terms of either Kramer transforms or Lejeune transforms, and these can be a little bit hard to deal with. So to try to answer the question I showed you at the beginning, I took a very naive approach, the combinatorial approach. Okay. So for simple random walk, so here that's just what we saw earlier. And so for a simple random walk, you can compute, well, this is straightforward, and you can find very easily the rate function. Okay. So if you know what this looks like, then you already know that the local central limit theorems I showed you earlier don't give the whole picture. Okay. So here's the first result. And I've never seen it in this level of detail, though you may have, and if you have, I'd be very happy to hear about it. Okay. So basically, we're looking at this probability, and we're thinking of x as going off to infinity as n goes to infinity. And basically, on a logarithmic scale, it's going to do this like a n for a ranging from 0 to 1. Okay. a equal to 0 is the case where x is just little o of n. And so that really covers most of the picture of what we tend to think of. So it certainly covers the cases we saw earlier. Then we can have some non-zero constant attached to the n. And the two last cases correspond to the case where a is equal to 1. Okay. And so this result gives asymptotics, well, okay, it gives exact asymptotics here, here, and then here there's this annoying cx of n, which I haven't really been able to tackle well, which gives us a bit of uncertainty of exactly what the multiplicative constant is, but it does give the right rate somehow. And then the obvious one here, if you think about it for a second, is the 1, because e to the phi of nx is e to minus this sum. If you take n and plug it into this sum, you get log 2. And so those are the two extreme probabilities, 1/2 to the n on both sides. At the farthest points that the walk can visit in time n. Okay, so the proof of this is straightforward and a bit painful at times, and I will spare you the painful part. But you can very easily see basically what's the painful part. This sort of comes out very quickly, and then you just have to somehow deal with the details of the polynomial corrections and the error terms. So, oops. Oh, all right, so I'll talk about the proof in a second, but here's what I think is maybe a nice way of thinking about it, which is that as you take your x and go out, if you increase a, so we know what happens at 1/2, we actually know what happens all the way up to 3/4. And then if you keep going, as long as a is less than 2n minus 1 over 2n, you know exactly how many terms you have in the sum right here. And so every time you hit a new ratio of an odd over an even, you have to add a term to your sum, which is an additional exponential term, less strong than all the previous ones, but it still adds a non-trivial, it contributes non-trivially to the probability. Okay, and if you've worked with rate functions, or if you're familiar with them, then you probably think that this is, you might think that this is completely trivial, at least that this part here is completely trivial, and to some extent it is, because I mean there's nothing really surprising here, because this thing is essentially the rate function given by Cramer's theorem. Okay. All right, and we'll see in the proof how this comes out, but it's okay. I'll go very quickly over the proof because it's likely to be boring for almost everybody here. So what's this probability? Well, we know that it's this, and then we just use Stirling's formula. And so essentially, if you look at this term here, all right, so there's a beta x which is related to the error term in Stirling's formula, and then you play with separately with the roots and all the rest. And all the rest essentially looks like this, and this is something we can expand exactly. Okay, and the way to expand it exactly is exactly like this. Okay. All right, so, I mean, this is, if you haven't thought about this before, this might be moderately interesting. I think it's less obvious what happens in 2 dimensions. Okay, and then last step of the proof. Okay, so in 2 dimensions, so All right, I almost didn't put this theorem on my slides because I realized yesterday or the day before that it's essentially contained in the next one, which is good enough to give a complete picture. But I still want to mention it because, and actually I want to talk about the proof of this a little bit, because this is what we would have to reproduce if we wanted to do this in higher dimensions. Okay. So what does it say? It says that if we take basically points that are of a distance, so all the logs you can, the logs are there for a reason. I didn't choose not to just write little O terms for no particular reason. They're here because you need logs on one end and logs on the other hand to somehow work out the right way. But essentially think of this as being little o of n, or little o of n squared here. And then here, this is a condition that's satisfied inside the disk of radius n to the 3/4. Well, very slightly less than n to the 3/4, and this is actually going to be important. And in fact, so okay, so what's the picture? So we have, all right, so we can draw a few of these. So root n is where we have the Brownian regime. It turns out that we can actually go to n to the 3/4 and still essentially have the Brownian regime. And then somewhere out here we have, are we in 2 dimensions already? Yes, okay. Okay, and then this here is basically the set of attainable points by 2-dimensional simple random walk. So this expression here holds inside this disk, or actually something slightly smaller than this, and we also have this region here covered. So here we have exact asymptotics. Okay. I also have exact asymptotics for the rest, and you may, and I don't want to write them down because they're very messy, and you can, and somehow hard to characterize nicely in terms of x and y. So you'll see in the proof what those terms might be, and you'll also see why they somehow don't, why they disappear in this region here. And by the way, okay, so this looks pretty big, but in reality, as n gets bigger, this really becomes very small somehow. So
yeah. Picture, it looks like
oh, is it?
Line x close, line x rather than line x far apart.
Thanks, you're right. So the picture was right until I started shading. Thanks. Yeah. Okay, great. Okay, so what does this look like? Well, so basically what happens, well, okay, I'll talk a bit more about what this represents geometrically later when we have another version of this theorem, so an equivalent version, which works for the entire, well, it's essentially for the entire square here. So let's come back to that in a minute, but let me just say a few words about the proof. And again, the main reason I want to do this is that the proof that works for the other nicer theorem works only in 2 dimensions. And so if one wanted to try to attack this in higher dimensions, one would have to follow sort of, well, the only thing I can think of, the only way I can think of doing this would be by sort of following this approach. So okay, so to keep things simple, let's think of y as always being greater than x, and let n1 be the number of steps that our two-dimensional random walk takes in the horizontal direction. Then we can basically condition on the number of steps taking in the horizontal direction. And that gives us a one-dimensional simple random walk in the horizontal direction. And we also have a vertical one with the remaining steps. And sum over all the possible choices of numbers of steps taking in the horizontal direction. So the expected value of that is more or less, where is this? Oh, we don't have this yet. Okay. Yeah, the expected value of this is more or less n over 2, so I'm centering everything around n over 2, and then j is the deviation of that from that. Okay, so then it's just this product. And we can do the same thing in higher dimensions, except that in the proof, something that's easily compared to an integral in the two-dimensional case stops being easily computable in higher dimensions. Okay. So the question of the distribution of the number of the probabilities of the walk taking a certain number of steps in the horizontal direction is essentially one-dimensional simple random walk problem. And so one can show, as in the one-dimensional case, that this is what one gets. And then, okay, so this looks pretty bad. But okay, so then what we have to do is basically take a one-dimensional walk in either direction. The number of steps is fixed, and so we again apply, in this case we apply exactly the one-dimensional result. Okay, so we get this. It looks maybe slightly, well, better or worse according to your point of view, but this is a bit more manageable. Well, this will be a bit more manageable. And the error terms, we're going to focus on j's being little o of n and x being little o of n as well. So, so this again is an exact asymptotic statement. All right, so we do it for the x's, we do it for the y's, and then we put everything together. All right, so this is the probability that in time n, two-dimensional random walks gets to the point xy while taking n over 2 plus j steps in the horizontal direction. Okay, so now what we have to do is sum all this. So this is slightly nasty because we have a double sum here. So we have two sums with different indices, but then we have a j in here over which we'll have to sum as well later. And so that makes things a bit complicated. But so here's basically what each of these represents. Okay. And so then what we have to do is sum over j. Okay. So then the idea is going to be to separate the sum into a dominant part which will be more manageable, which can actually be estimated precisely. In other words, we can obtain asymptotics. And another one which we can show is smaller and is hard to compute exactly, but we don't need to because it's pretty easy to show that it's smaller. Okay, so this is most of this is just a repeat of what we had before. The key idea is that P of j, which is basically this, has a unique maximum at j naught, which is minus y squared minus x squared over 2n. And so that means that for a given point xy, the most likely number of horizontal steps taken by the random walk as it's going to that point in time n is n over 2 minus y squared minus x squared over 2n. Okay, and the reason things are nice when y squared minus x squared is less than or equal to n to the 3/2 is because in that case j is in this sum, which is the one that's manageable. Okay. So what's P of J naught? Well, if we know what P of J naught is, then we basically know what the log asymptotic result should be. Okay. And, well, P of nxy J naught is this, which looks bad, but the good news is that of all of these terms in these two sums, there's really only one that's not little o of 1. So only one that's relevant. And that's the one that corresponds to k equal to 0. Okay, and so that's how we get basically the log asymptotic result, again, in this somewhat limited region here. Okay. All right, so this really wasn't necessary, except if you want to have an idea of how to do it in higher dimensions, because if we have an exact asymptotic result in one dimension, we can get an exact asymptotic result in 2 dimensions. And the idea is, well, change your lattice a little bit. In other words, shrink it by a factor of root 2 and rotate it by pi over 4. Now we can take a one-dimensional simple random walk going in this direction and a one-dimensional simple random walk going in this direction. Call them S1 and S2. Let them be independent. Then this is a two-dimensional simple random walk. And, well, it's magic. And it's not so clear why it should work in 2 dimensions and not in higher dimensions, but it doesn't. So this nice trick, which makes things very simple in 2 dimensions, at least in this case, doesn't work in higher dimensions. But so why is it useful? Because, well, now we have 2 independent simple random walks. We have a result for each, and we just multiply. And so if we do this, we get this here. And this sort of suggests that the right way to think about 2-dimensional random walk is not by thinking of the 2 axes as being horizontal and vertical, but thinking about this change of variables here, x plus y and y minus x. So the picture we get in this case, so again, so we have, all right, so in this case, let me just draw. I have other things that don't exactly look like circles in a second, so my circle should at least be round. Okay, so what happens is that every time we hit a new ball. So the question here is when, which of these terms count and which don't. And so, well, it's easy to draw a picture for that. Every time our point xy gets to an L2L ball of this radius, and it's a ball with axes x plus y and x minus y, a new term appears in here. So, so it sort of shows how one transitions from the disk to the square. Well, this is probably the. It looks very much like the picture you've seen of, you know, a sequence of LP circles as P grows. So the next one will look a bit like that. And we'll have sort of a smooth transition from the circle to the square. along these L to L balls. Okay, so this is what I mentioned earlier. So the proof just looks at one-dimensional random walks in the two diagonal directions, puts them together, and then basically multiplies the results, well, multiplies the asymptotic expressions for this one, and just plugs in the right values of x and y. Okay. So what this shows is that, well, and we'll see it in a second, maybe you see it already, is that when you get more or less to distance n to the 3/4, and now by distance I really mean L for distance. When you get to distance n to the 3/4, the regime changes. Okay. So here's the result. If you're within a disk of radius little o of n to the 3/4, it's probably true for any little o of n to the 3/4. Well, okay. But all right, we can get very close to 3/4. We have approximately rotational symmetry. Okay, so what do I mean by that? I mean that if we take any 2 points that are at the distance from the origin that's separated by at most 1, as n goes to infinity, the probabilities are the same. So within a disk of radius slightly less than n to the 3/4, we have approximate rotational symmetry, and outside of a disk of radius n to the 3/4, and you can divide that by any constant you want, we don't, because we have 2 points. We can find points that are at more or less the same distance from the origin, for which the ratio of the probabilities of being at that point at time n goes to 0. So some points outside of the disk of radius n to the 3/4, and now I mean really L2 disk, are much more likely to be hit than others. Okay, this is immediate from the 2 theorems we saw earlier. So this was the first one, and well, all we have to do is take x squared plus y squared to be r squared, plug it in here, and we get that we always get exactly the same thing with an error term. So I'm not. This is if it's r. Well, if it's r plus epsilon, then the epsilon disappears in the limit. Okay. So here it only depends on r. In the case where we're outside of the disk of radius 3/4, well, let's just take 2 points and see what happens. And so if we plug these 2 points into this expression, we get in one case this. In the other case, almost the same thing, except for a 2 to the L right here, which starts to matter as soon as we get to the second term in here. When does that matter? Well, as soon as r is of order n to the 3/4. Okay, so.
You would need it bigger than some constant in the 3/4, right?
It works with the constant 1, I think.
They work
But,
with constant.
right,
Yeah,
but with any other constant as well. As long as it's a constant and nothing that's Okay, so all right. Let me just get back to the original question, which was what is for two-dimensional simple random walk the probability that Sn is bigger than or equal to R. Well, okay. So here's the lazy way of answering the question. Take logs. If you take logs, then really the only thing that matters is the point at which the probability, the point at distance r for which S is most likely to be, at which S is most likely to be at time n, and so you get, it turns out that it's R0, and plug that in. All the other terms on the circle will add something to it, but whatever they add in the, once we take logarithms has no effect. So we're left with this. So, okay, so here we see that basically every time R gets to a power which is that of an odd number over the next even number, we get a new term in our exponential. Michael?
Sorry, what's R?
So R is just any real number. Okay. It stops. Okay, so this stops working at n. The good news is
don't understand
you mean in the last row?
Yeah, I
yes.
can see where R
Yes. R is n here.
Ah.
Okay, it's a typo. Yeah.
Okay.
So if R is n, then we get exactly n log 4, and if we take e to the minus that, we get exactly 1/4 to the n, which corresponds to the 4 corners of the square. Okay, and I guess a tradition was started yesterday to make the last talk of the day very short, so I'll continue in that tradition.
Okay, so that means we have plenty of time for questions.
Is that a hint that I need to write another book?
Oh, what happened? That was not my intention. No, yeah, okay. So if you come very close, there's some light yellow here, which on my computer was highly visible, and here apparently is not. Okay, yeah, that didn't come out exactly the way I wanted.
Right, any other questions?
But maybe you should write another book.
Okay, so before we thank Christian again, Michael has some announcement.
Okay, so we have the banquet tonight, and I wanted to make a couple comments about the banquet.